Hey everyone, welcome back to the channel, and it's been a while since I made my last video, but I'm really excited to be back, and today we're going to do something a little bit more practical. This is going to be a problem-solving episode, and we're going to go through a few exercises based on the material that we have covered before in our previous videos. So if you haven't seen those ones, feel free to check them out, just to make sure that you are following along smoothly. And alright, let's jump right in. So there are a few problems that I'm planning to consider in this episode. They are proof-based problems, but in order to get started with them, you have to understand the basic axioms of the probability theory. Of course, we have already considered them. We have already covered all of those axioms in our previous videos, but I would like to refresh your memory quickly and go over them again, just to make sure that we're all aligned here. There are three very important axioms. So the first axiom basically states that for any event A from some kind of collection or from as a subset of the sample space, let me just show you, for any possible event A, which is the subset of the sample space, obviously, or it is also the element of the collection, the probability of this event is greater than or equal to 0, which is not negative, which is quite obvious because the probability cannot be negative, and that's something that makes total sense. And this is basically it. That's the first axiom. The second axiom is, let me just designate that as first. The second axiom is that for the certain event, for the shared event, as we name it, the probability of this certain event is 1. Well, this is basically the sample space. And the axiom 3 is that if we have two sets, well, let's say events actually, event A and event A2, which belong to a collection C, the probability of their union, event A and event A2, is actually the sum of probability A1 plus A2. Well, in case if they are mutually exclusive, and I really hope you remember what the mutually exclusive means. Mutually exclusive basically means that these two events cannot happen at the same time. So if you have, let's say, event A, like tossing a coin and coming up with the head, like when you're tossing your coin, getting the head, and the event A2 is like getting the tail. Oops. Obviously, those events are mutually exclusive. They cannot happen simultaneously when you're just tossing a coin once or coming up only with one specific outcome, either tail or the head. So that's pretty much obvious. And in that case, the sum of those events, the sum of probabilities of those events, this is the probability that one of them happened, well, either A or A2. Well, so that's basically three axioms. And now let's get started with our problems. So the first problem that I would like to consider here in this episode, which is pretty simple, we need to prove that if we have two events, let's say event A and event A2, and event A is a subset of event 2, in that case, let's say we have to prove, in that case, the probability of event A is less than or equal to the probability of event A2, and the probability of event A2 minus event A1 equals to probability of event A2 minus probability of event A1, like this. P of A2, P of A1. So let's get started with proving this. If event A1 is the subset of event A2, in that case, A2 basically can be considered as event A1 union event A2 minus event A1, which is pretty obvious. Now let's try to visualize this sets. Let's say we have the set A2 and we have the set A1, which is the event A1, which is completely inside the A2. In that case, obviously, the set A2 minus A1 is the space, which is obviously inside the A2, but not inside the A1. So it becomes apparent that A2 minus A1 is mutually exclusive with A1, which gives you the empty set, which is pretty cool because we can leverage the axiom 3, and now we can just say that probability of A2 minus A1 union A1, and they are mutually exclusive, is the sum of probabilities A2 minus A1 plus the probability of A1, because again, they're mutually exclusive. Well, the first thing they can notice here is that this union is actually the set A2. So that's going to be equal to A2. And now you have E of A2 equals to P of A2 minus A1 plus P of A1. And here, at this point, you can see that this term is either empty or this is positive. And this follows from our first axiom that should be positive, or non-negative at least. Well, in that case, you have that P of A2 obviously is larger than or equal to P of A1. Because if this term is positive, then this term will be greater than or equal to P of A1. Oh, I hate this mathematical suggestions. How to turn off. I hate them. So that's pretty much it. You already proved that. The second statement that you have to prove here is that the probability of the difference of those sets is the difference of those probabilities, which is something that we already proved actually, because from this expression you can easily derive that the probability of A2 minus A1 is essentially the probability of PA2 minus P of A1. And that's it. Everything is proved. That was pretty simple. Now let's get to the second problem. So this, for a second problem, we have to prove that the probability of the event, any event obviously, of A is less than or equal to 1 or greater than or equal to 0. How to prove this? Well, that's pretty much simple. Obviously, based on our first axiom, we can say that the probability of any event is non-negative. That's already proved. And also you can see that event A is the subset of sample space, obviously, by the definition, which means that the probability of event S is greater than or equal to the probability of A. Based on this proof, based on our previous problem, we already know that the probability of S, which is a certain or sure event, is 1. That being said, the probability of our event A is less than 1, but at the same time, the probability of event A is greater than or equal to 0. So that's pretty much it. We just use our basic axioms here. And one more problem for today is that we need to find the probability of the complementary event, right? The probability of the complementary event equals to 1 minus P of A, but we have to prove this. And in order to solve this problem, it would be easier to visualize that. Suppose we have the sample space, just sample space S. And now you have the set A, which is the set A. And the complementary set is everything which is beyond the set A. So you just have to calculate the probability of the event A prime. Those two events are mutually exclusive. And the event A is basically S minus event A. Well, I mean, event A prime is S minus A. So you can say that A prime is the S minus A because they are mutually exclusive. And event A is actually inside the event S, the sample space. And based on our previously proved problem, this should be the exact same thing here. P of S minus P of A, which is P of S minus A. And that's pretty much it. We just have to show that the probability of S equals 1. And in that case, probability of A complementary would be P of S minus P of A, which would be 1 minus P of A. And that's pretty much it. Alright, that's it for today's problem solving session. I hope working through these examples help you understand the concept a little bit better and give you more confidence with the probability. And thank you for watching. See you in the next episode.